Finite element analysis, or FEA, is a powerful tool for evaluating structural performance under realistic operating conditions. At Predictive Engineering, we use FEA to simulate stress, vibration, and fatigue across a wide range of industrial equipment to determine potential weak points, longevity, and reliability, sometimes before the initial prototype is even made. This FEA-driven approach helps us catch design flaws early, avoid over-engineering, and confirm compliance with ASME and customer specs before fabrication. Every project begins with a well-defined problem statement. We start by identifying the loading conditions, code requirements, and service expectations that drive the analysis objectives. Next, we import and clean the CAD model in SimCenter FEMAP. This step ensures that the geometry is FEA ready with unnecessary features removed and critical details preserved. Once the geometry is prepped, we generate a high-quality mesh on the structure. The mesh density is refined in areas where stress gradients are expected. We then apply realistic boundary conditions and mechanical loads, pressure, bolt preload, thermal effects, or gravity based on the design requirements. Finally, we run the analysis using SimCenter Nastran. Results such as stress, deformation, and fatigue life are extracted and compared against ASME or client-defined limits to validate structural integrity. In this project, we conducted FEA to evaluate weight reduction strategies for a separator. We modeled both the baseline and modified designs using SimCenter FEMAP and solved them with Nastran. To improve computational efficiency, we used quad shell meshing and tested multiple plate thicknesses. We benchmarked the results against material yield limit to ensure structural safety. In the end, the optimized configuration achieved significant weight savings without compromising mechanical integrity. In another project, we performed a modal analysis to assess vibration characteristics. Using SimCenter FEMAP and Nastran, we modeled the tanks at multiple field levels to identify natural frequencies and mode shapes. The initial analysis revealed modes that could align with operational excitation. We then refined the design by adding stiffening rings which shifted the critical frequencies. A final validation confirmed that the updated design would reduce resonance risk and ensure reliable long-term operation. As part of our ongoing work supporting ASME design validation, we performed a detailed stress analysis on a blind flange to ensure compliance with ASME Section 8 Division 2. The model was built in SimCenter FEMAP using a high-quality solid mesh to ensure accurate stress distribution and realistic deformation behavior. We applied internal pressure, hydrostatic test conditions, and bolt preload as contact pressure on the gasket surface. We then compared membrane surface and peak stresses against ASME code limits. All results passed with satisfactory safety margins. This analysis gave the client confidence in the flange's reliability and helped streamline fabrication and code approval. Continuing our work with ASME code, we conducted a finite element analysis on an industrial agitator support to evaluate stress and fatigue under combined mechanical and pressure loading. The model was built in SimCenter FEMAP using appropriate elements. We applied pressure, axial, bending, and torsional loads and evaluated the results against ASME Section 8 Division 2 criteria. Fatigue life was assessed against the smooth bar design curves from ASME code and reported to the client. To learn more about our services and how we can support your digital prototype, visit us at predictiveengineering.com.